The comparison test is actually quite simple. I think the comparison test is that you have a sequence, or you have a series that forms from a sequence. Then you try to find another another series that is term by term larger or term by term smaller than the series that you want to test. Then you make comparisons. So this is what it is like. For example, if you ask to check a sequence of AN is converged or not. So you are given a sequence, a sequence of AN. Then the sequence of AN forms a series. Right? So sum of the sequence term AN is a series. You want to know, does this series converge or not? So what you do is that you try to think of another series where the another series that contains another series where the terms in the series is term by term larger than the series you want to test for convergence. Then if you can think of an sequence C such that the series of Cn converges, where each term in Cn is larger than An, then if Cn, the series of Cn converges, then so is the An converges. Okay, so I think it's kind of conceptually easy to understand. You want to prove this to be converged, you find an sequence that is term by term larger than the original sequence. Then if this converge, then this will converge as well. So like you have another situations where you have you are given a sequence and form and series. And in order to tell whether this converge or not, you have to be imaginative and try to come up with another sequence that form a series. And if you know that the new series called Dn is term by term smaller than the term in the series of An, then if this is divergent, then so is this is divergent. I think this is basically you can represent this very easily by now drawing a graph. Say, for example, you have S, which is the sum of An. So you can imagine that this An is like a term that is like, for example, that looks something like this. Okay, so here these are the An. Then if you have another another series called Bn, right? Bn, where Bn term is larger than this. B1 is larger than A1, B2 larger than A2, B3 larger than A3. Right? So this Bn is always on top of An. So if Bn, the series, converges, if Bn converge, that would simply means that the series of An converges. Okay, that is basically the idea. Likewise, if you have a term of say a series that is formed by term An that is like this, then you have another term called Bn, where Bn is term by term less than An. Right. So if this is another sequence called Bn, where Bn is always less than An term by term. So the Bn is sitting downstairs, right? So if the Bn series diverges, if it diverges, then because all the An are sitting on top or above of Bn, so if Bn diverges, then An would diverge as well. So you check the convergence of an series by comparing it to a sequence that is known for its convergence. So here, to apply the comparison test, you have to have some kind of idea what sequence, what series diverges, what series converges. Then you have to pull out that series and compare it to the series that you want to find the convergence. So example is this. So let us look at this very simple series. 5 over 5n minus 1. Then you just make some rearrangement. Then this series, the term in the series become 1 over n minus 1 over 5. Right? So this is what you want to see whether it converges or not. So what you do is you compare it to another known sequence. So you compare it to harmonic series, right? So harmonic series here is a reference. You know harmonic series is divergent. You compare the terms in the sequence to the terms in the harmonic sequence. So harmonic sequence is definitely larger than, sorry, this term is larger than the harmonic series. So harmonic series is always sitting on the bottom, and this term, this sequence is sitting on top of the harmonic series. And we know harmonic series diverges. Therefore, if the harmonic series diverges, so is this term, this sequence also diverges. So with this, then we say the series like this is divergent when you compare it to the harmonic series. So here the trick is you must have some basic reference in your repository. You need to know to what series this sequence has to be compared to. Right? So you need to know I have my P series, I have my, say, I think harmonic series is one of the most useful series that represent a divergent series. Then other than that, sometimes you also want to say compare it to some other sequence that is convergent. So that you have to be creative to come up with a sequence that is known to either converge or diverge. So for example here, you look at this series. This series is sum of 1 over n factorial. Then you compare this series to a geometric series. You know geometric series is convergent, right? That's why I keep on telling you in the beginning of this lecture, we have learned harmonic series which is divergent. We have learned geometric series which is convergent. Why do I need to tell you that? Because we are going to use the geometric series as an comparison, as a reference to compare it with another sequence. So here, this is a sequence we want to find we want to find the convergence of this. So what you do is you compare this series to an geometric series. So this is a geometric series with a ratio of r equals to 1, r equals to half, with an addition of number of 1. So term by term, you find that this geometric series is larger than the series. Right? So you have 1 over factorial, you have 2 over factorial, you have 3 over factorial. So you look at this one, then you come to the conclusion that if you compare this series with an geometric series, and term by term, this is less than this term. So for example, I think this is equals, this term is less than this term is less than this term. This 2 factorial is 2 times 2. 3 factorial is 9. I think this is 1 over 4. So this is 6, right? So 3 factorial is 6. This is 4. So if you look at this one, this is 1 over 4 factorial. So 1 over 4 factorial will be less than 1 over 2 power 3. So therefore, this is term by term larger than this series. And we know a geometric series, in this case, converges. So therefore, if the geometric series converges, then this term, when it compared to a geometric series, this term must also converge, because term by term, this series is less than the geometric series. Okay, you got me? Right. So sometimes this kind of test is a bit difficult to apply, because you have to be imaginative and be creative to compare to a series where it's it's a result of convergence. So you look at this one. If I don't tell you what to compare to, you have to think, right? What should I compare to? Right? But if you are very creative, you know that you compare this to a geometric series. So in a sense, this kind of comparison test is not as easy, because you have to be creative to come up with a series that you know is result. If I don't tell you what to compare to, then sometimes it will be difficult to come up with the correct comparison. Okay, so here we have another easier to use test. called limit comparison test. You don't compare directly to an sequence. I think this is easier than this one. What you do is, yes, you look at this one. It comprises of three parts: the first part, second part, and third part. But just let us look at the first part. Say if you have an series which is comprised of the term an and bn, and the condition is that the term an and bn has to be positive for all n. Then what you do is you if you find that the limit of ratio of an over bn is a constant and is positive when n goes to infinity, then the fate of the series an and bn are tied together. Right? If the ratio of the two terms is finite when n goes to infinity, then what you can conclude is that if bn converge, then an will converge. If an diverge, then bn will diverge. I think this is what it says. But actually, in order to apply this theorem, it's actually quite simple. So what you do is this: if you're given a series like this, so first of all, you check the limit behavior, the limiting behaviors of the sequence. Then you divide the sequence by the limiting behaviors of the sequence. Then you see whether they converge. I mean, the ratio converge to a constant or not. Then you'll be able to tell the convergence of the sequence. So let us try to explain how to apply this. So let us look at example 2. Say part B. Part B is another series of 1 over 2n minus 1. So here the series is the summation of 1 over 2 power n minus 1. So I think this is the next example. 1 over 2n minus 1. So we are going to apply the same tricks. So here I will call this as the summation of an, where an is the term of 1 over 2n minus 1. So let us try to figure out what bn is. I have to invent an bn. So I will take bn as the limiting behavior of an when n goes to infinity. So you look at an, you have to be able to tell what is the behavior of an when n goes to infinity. When n goes to infinity very, very large, then 2 power n is always much, much larger than 2n. Therefore, you drop the minus 1 in the limit when n become very, very large. Therefore, you come to the conclusion that you can choose bn to be 1 over 2 power n. So then you type up an or bn and check for their limit. So what you get, you always get n constant, right? Because in this limit, when n goes to infinity, the behaviors of an is chosen to be equals to bn. Therefore, it's also equals to a number which is equals to 1. So now you have tied up the fate of an to bn. Now we want to know whether the series of an converge or not. You don't look at it now. You don't look at an. You just look at summation of bn. Now bn is 1 of 2 power n. So again, this is a geometric series. It's also a p series. I think this is a geometric series. Geometric series with ratio r equals to half. Therefore, this geometric series converges. Since an and bn, their fate are tied up together. Therefore, the convergence of bn infer the convergence of an. So that is how the part B of the question is solved. So that is the example of the applications of the of this what we call limit comparison test. So again, the limit comparison test is a very convenient tool that allows you to answer the question whether a given sequence, a given series is convergent or divergent. Okay, so that's the solutions that is the tools, the tricks that we have already that we have discussed this morning. Okay, so we have learned this integral test. We also learned comparison test and limit comparison test. So there will be another tricks to help you to answer the questions of the convergence of an series uh, in the tomorrow's discussion. I think this is called the ratio test. So ratio test is very easy. So probably we'll be able to cover ratio test in the first part of the discussion tomorrow. But then we're going to talk about the alternating series together with the ratio test. So I'll see you again tomorrow.